Hi everyone, it's Mr. H here. Today we're going to talk about critical angle and total internal reflection. What we're going to begin by doing is seeing how light passes from one medium to another, how it actually changes. And so if we were in the classroom, we would go and do this experiment together in the class. However, in this particular case, I've sourced a video by Quantum Boff, and I'll include the full link to the video below. But let's just see what happens as he changes this angle. You can see here that light is coming from a ray box. The light ray is coming in through this glass. It's a circular, half semicircular piece of glass, and then it's going to come out the other side. And so as I change the angle that light goes into the glass at, because it's circular, the angle that it enters into the glass, if it was coming from over here, it's going to come in and go straight into the glass. And so the angle would be along the normal, and the angle wouldn't change even though the speed would. Where the angle will change is when it's exiting this side of the glass. As it does that, it's going to bend, and we know that when it slows down initially, it bends towards the normal, but when it speeds up as it enters back into air, it's going to bend away from the normal. So what we're going to see is this angle, let's say an angle like this one here, so light ray comes in like this, it's actually going to bend away from the normal, and the angle that we're going to get coming out of the glass is actually bigger. So here we go, we're changing that angle. It's hard to see at first, but you can see that what's happening, focusing on this light ray right there, is the angle here, let's look at about 20 degrees. There we are, 20 degrees angle of incidence, but the angle of refraction was about 35 degrees at that point. And you can see that this angle is always going to be bigger than this angle down here. Now the question is, what's going to happen when it gets big enough that this angle is 90 degrees? Let's see. The refracted ray has completely disappeared. In fact, right along here, the refracted ray has become just the reflected ray. You saw that reflected ray get brighter and brighter. And now as I continue to make that angle bigger and bigger, all we have is the reflected ray. And so this is what we call total internal reflection. And so this angle, right where this becomes 90 degrees, the angle here up to this, which is about 42 degrees in this particular case, is called the critical angle. Now that's going to have a different angle depending on what the material is, but that's for glass, a critical angle of 42 degrees. So let's just together summarize what we just saw. When light travels from one medium to another, some is usually refracted and some is usually reflected, and we saw that in the semicircle. This is called partial reflection and partial refraction. Part of the light ray is reflected, part of it is refracted. Now you probably noticed the closer you got to that critical angle, the more reflection happened and the less refraction happened. And that's interesting because the light rays are reflecting more and not refracting as much. When light travels into a less dense medium, the critical angle can be reached with the angle of refraction is 90 degrees. What that means here is you can see in this middle part of the diagram below that the angle there is 90 degrees. And so when this refracted ray is at 90 degrees, this is the critical angle measured down here to the normal, because this is the normal here. Goes on to say this, if the angle of incidence is bigger than the critical angle, all of the light is reflected, as we see in this particular case. Let's call this case 3. In the second case, we saw that critical angle reached, and in the first case, we saw both the reflected and the refracted rays. We have partial reflection, partial refraction. And so notice that this will only happen if we're moving from a denser material to a less dense material. This will not happen going from a less dense material to a more dense material. Let's see this if I give you the example of going from air to water. So instead of working upwards, it looks in the case on the left here, we're going to go downwards. So here's the light ray coming in, going from air into water. And what we know happens as you enter a more dense material, based on the analogy yesterday we had of the two wheels hitting mud, for example, that is going to bend towards the normal. So this angle of refraction is actually smaller than that angle of incidence. And so you can see that regardless of how big that angle of incidence gets, even if I get almost 90 degrees, so there's the angle of incidence, it's really large going from air to water. If I have this angle is still going to be relatively small. There's my refracted ray there. it's never going to reach a critical point. It can only happen going from more dense to less dense material. So this is actually used more often than you might think, and one of the ways we use it is in binoculars. Binoculars, they can sometimes contain a series of lenses, only lenses, but very often they contain also a couple of prisms on each eye. And what that does is the light comes in right along the normal into the prism on this side. There's the normal, so it's coming at 90 degrees to both the air side and to the prism side. And then what happens here is it encounters air at an angle of 45 degrees, but it's past the critical angle, so what we get is total internal reflection. The same thing happens over here, total internal reflection, and then again it comes out along the normal, so it's not going to bend at all, it's just going to speed up when it hits the air again. And then it's going to do the same thing against these two surfaces, total internal reflection, until it comes back to your eye through another series of lenses over here. It's going to do the exact same thing in the other eye. The other example that we encounter more often than we might think is fiber optic cables. The basis of a fiber optic cable is it's made of glass, and it's able to bend slightly without breaking. It's surrounded by some insulation of some sort. But for the simplicity of just considering what it is, let's consider it just as a glass tube with air around it. Glass is more dense than the air around it, which means that we can get total internal reflection if the angle is big enough. And so even as we bend this glass, if this angle is big enough, I think the biggest angle, or the smallest angle that we have here is this one right there, that is still a large enough of an angle that there will be no refracted ray. This is actually the basis of your internet communication. Yes, we can send electromagnetic waves through the air, but most of what is sent through the internet is actually sent through these fiber optic cables. Everything you download or upload is a light beam that's sent through a fiber optic cable, and it's allowed it to travel very long distances very easily. In fact, there's a fiber optic cable to send information across the oceans. You can literally, it's buried on the bottom of the oceans, and you can see that if you research it a little bit, you can check it out. Really fascinating application of this total internal reflection. Last but not least, we're just going to consider a few examples of optical phenomena in nature. Rainbows are a great example of this idea of refraction and reflection and total internal reflection. In fact, you can see here, just from the diagram there on the right side, that you have white light coming from the sun, and we know white light is made up of all the colors of the rainbow. So here's the sun over here, all right, and here's you're standing right here. So the sun has to be behind you, and the white light has to be shining from behind you, and the rainbow is being formed in front of you, hence the water droplets are in front of you. And so what happens is that white light comes in, it begins to refract as it bends into the water droplets. We get total internal reflection on the back of that water droplet. It refracts again, which splits the light into more distinct colors as it exits the water droplet. And then these distinct colors make it to our eye, and we see what looks like a rainbow, because it is a rainbow, but not physically there. So the conditions that must be met in that case is that it must be raining when the sunlight hits, and the sun must be behind you. You'll notice the same thing if you look into, for example, a waterfall. If the waterfall's in front of you and the sun's behind you, you get the same effect for the exact same reasons. There are a few other optical phenomena that I've included here that you can get into more detail if you're interested in your project for this unit. One is sundogs. If you're up really early and it's really cold outside, what you'll occasionally see is you'll see what looks like these really bright spots on both sides of the sun. Kind of looks like you have these little glowing bits, and that's because what's happening is the light is actually reflecting off of ice crystals in the air along the ground. So some people thought it kind of looks like a dog that's howling, and so that's why they call them sundogs. We get halos when we get really cold light, really cold days, and we don't only have the sundog, but we get the ice crystals all the way around the sun forming. That's a halo. Another example that we see is shimmering, and that's when hot air above an object causes it to appear moving. You've probably seen on a very hot day, when you look out at a very area that's paved and very dark that absorbs a lot of sunlight, you'll notice that it seems that the light is kind of moving. And that's because you've got cold air from the atmosphere meeting very hot air close to the ground. And as those interact, because air is a gas, they're going to interact very rapidly, and they're going to cause it to look like it's moving. A mirage is an example when we see the bending of light passing through layers of air at different temperatures. Warmer air is less dense, causing light rays to curve away from the normal. And so what you see in this case is what looks to be a mirage. It looks like there is water all over the road, when in fact there is not. If you were someone standing right over here, what you would see is let's say the sun is over here, so some light would come directly from the sun right to you. That's often what would happen. But in the case where we have very hot air is less dense, and light actually moves through it faster. And so what the light's going to do is it's actually going to do this. It's going to bend, and it's going to get to you faster that way. And so as it bends, it's actually reflecting what's in the sky and coming to you quicker. And so you're seeing what is the sky rather than actual water. The last example I want to talk briefly about is apparent depth. You know probably from example that if you drop something in a shallow pool and you try to reach down and get it, it looks like it's shallower than it actually is. You notice you have to reach down deeper than you actually think you do. And that's because of apparent depth. You see from this diagram right here that if something's sitting in the bottom of a pool, what happens is because its water is more dense than air, it's going to bend away from the normal. The light rays from that object are going to bend away from the normal as they exit the water going into the air. Hence, this angle right here, called as theta 1, is much smaller than theta 2. And so that's the principle behind apparent depth. And it's also the principle behind the disappearing penny, if you've seen that. Hope that's helpful. If you have any questions, as always, feel free to ask for help.